let's talk a little bit about chemical reactions. And chemical reactions are a very big deal. Without chemical reactions, you or I would not exist. In your body right now, there are countless chemical reactions going on every second. Without chemical reactions, we would have no life. We would not even have the universe as we know it. So what are chemical reactions? Well, they're any time that you have bonds being formed or broken between atoms or molecules. So what are we talking about there? Well, this is maybe one of the most fundamental chemical reactions. Once again, if this one never occurred, we'd be in trouble. We would not have any water. But let's think about what it is actually describing. So over here on the left-hand side, we have the reactants. Let me write that down. So here we have the reactants. These are the molecules that are going to react. And then we have an arrow that moves us to the product. So let me do that in a different color. So we have an arrow that moves us to the product, or we could say the products. And so what are the reactants here? Well, we have molecular hydrogen and we have molecular oxygen. Now, why did I say molecular hydrogen? Because molecular hydrogen, which is the state that you would typically find hydrogen in if you just have it by itself, is actually made up of two hydrogen atoms. You see it right over here. 1, 2 hydrogen atoms. And what we have, in order to have this reaction, you don't just need one molecular hydrogen and one molecule of hydrogen, one molecule of oxygen. For this reaction to happen, you actually have 2 molecules of molecular hydrogen. So this is actually made up of 4 hydrogen atoms. So let me make this clear. So this right over here, this is 2 molecules of molecular hydrogen, and that's why we have the 2 right out front of the H sub 2. This little subscript 2 tells us there's 2 of the hydrogen atoms in this molecule, and then this big white 2 that we have right over here, that tells us that we're dealing with 2 of those molecules for this reaction to happen, that we need 2 of these molecules for every molecule of molecular oxygen. And molecular oxygen, once again, this is composed of 2 oxygen atoms. 1, 2. So under the right conditions, so you need a little bit of energy to make this happen. If under the right conditions, these 2 things are going to react, and actually it's very, very reactive, molecular hydrogen, molecular oxygen, so much so that it's actually used for rocket fuel, you are going to produce 2 molecules of water. We see that right over here. And look, I did not create or destroy any atoms. I had one oxygen atom here. It was part of the oxygen molecule right here. And then I have the second one right over here now. Now they are part of separate molecules. I had 1, 2, 3, 4 hydrogens. I now have 1, 2, 3, 4 hydrogens, just like that. And actually this produces so we could say some energy, and I'm being inexact right over here, some energy. And then we could say a lot of energy, a lot of energy. So this is a reaction that you just give it a little bit of a kickstart, and it really wants to happen. A lot of energy. So one thing that you might wonder, and this is something that I first wondered when I learned about reactions, well, how does this happen? Is this a very organized thing? Do these molecules somehow know to react with each other? And the answer is no. Chemistry is an incredibly messy thing. You have these things bouncing around. They have energy. They're bouncing around all over the place. And actually, when you provide energy, they're going to bounce around even more rigorously enough so that they collide in the right way, so that they break their old bonds and then they form these new bonds. So whenever you see these reactions in biology or chemistry class, keep that in mind. It looks all neat and organized, but in a real system, these are all of these things just bouncing around in all different crazy ways. And that's why energy is an important thing here, because the more energy you apply to the system, the more that they're going to bounce around, the more that they're going to interact with each other. The more reactants you put in, the more chance that they're going to bounce around and be able to react with each other. Now, I'm going to introduce another word that you're going to see in chemistry a lot. This water, we have 2 water molecules here. We could call them molecules, but since they are actually made up of 2 or more different elements, we could also call this a compound. So water is, you could call it a molecule or you could call it a compound. So this is a molecule or compound, while this molecular hydrogen, you would not call this a compound. And this molecular oxygen, of course, it's a molecule, but you would not call it a compound either. And just to get an appreciation of how much energy this produces, let me show you this picture right over here. That's the space shuttle. And this big tank right over here, this big tank contains a bunch of liquid oxygen and hydrogen. And to create this incredible amount of energy, it actually just you mix the two together with a little bit of energy, and then you produce a ton of energy that makes the rocket, that makes the space shuttle. Well, the space shuttle's been discontinued now, but back when they did it to make it get its necessary velocity. Now let's talk about the idea. So this reaction strongly goes in the direction of going to water, but it can actually go the other way. But it's very, very hard for it to go the other way. So in general, we would consider this to be an irreversible reaction, even though it is, irreversible sounds like, hey, you can't go the other way. It just really means that it's very unlikely to go the other way. You have to supply a lot of energy to go the other way. To make this reaction go the other way, you'd have to do something called electrolysis. You're providing energy, et cetera, et cetera. But in general, the way that this is written, because the arrow is only pointing in one direction, this is implying that it is irreversible. Irreversible, which probably makes you think, well, what about reversible reactions? And I have an example of a reversible reaction right over here. I have one bicarbonate ion, and the word ion, that's just to use to describe any molecule or atom that has an imbalance of electrons or protons that cause it to have a net charge. So this makes this an ion, and actually right over here, this is a hydrogen. This is a hydrogen ion right over here. Both of these are charged. One has a positive charge, one has a negative charge, but they are both ions. And this reaction right over here, you have the bicarbonate ion that looks something like this. This is just my hand drawing of it. Reacting with a hydrogen ion. It's really a hydrogen atom that has lost its electron. So some people would even say this is a proton right over here. This is an equilibrium reaction where it can form carbonic acid. And notice all that's happening is this hydrogen is attaching to one of the oxygens over here. And this is an equilibrium because if in an actual solution, it's going back and forth. If you actually provide more reactants, you're going to go more in that direction. If you provide more of the products over here, then you're going to go in that direction. And so in an actual in an actual environment, in an actual system, it's constantly going back and forth between these two things, and different reversible reactions might tend to one side or the other. If you provide more of the stuff on one side, it might go more in the other direction because they're going to be more likely to interact. Or if you provide more of this, it might go in the other direction because these might more likely react with their surroundings or disassociate in some way. Now, just to get a sense of, it's nice to kind of, are these just some random letters that I wrote here? Carbonic acid is actually an incredibly important molecule, or we could call it a compound because it's made up of two or more elements in living systems, and in fact, even in the environment, and even when you go out to get some fast food. When you have carbonated drinks, it has carbonic acid in it that disassociates into carbon dioxide, and that carbon dioxide is what you see bubbling up. Carbonic acid is incredibly important in how your body deals with excess carbon dioxide in its bloodstream. Carbonic acid is involved in the oceans taking up carbon dioxide from the atmosphere. So when you're studying chemistry, especially in the context of biology, these aren't just, interesting things that seem very academic. These are affecting your real life and your body and your environment.